Hi guys, quick video to show you how to use the Wave Information Study portal. And this is how we look at computer output from the simulations of the Army Corps' Wave Information Studies computer model, which gives you wave information for all U.S. coasts. So you go to the Wis homepage, so you can see the URL up here, or you can just Google it. We go to the Wis portal, so if you Google Wis portal, you'll just go right to it. So it'll show you a map of all the U.S. coasts, and you will see little icons everywhere that you can get output from the model. So you can get offshore output, you can get nearshore output, you can see you get Hawaii, the Marshall Islands, I think this might be Guam over here, so it's super cool. All U.S. coasts. Puerto Rico is down here, but they have a lot of the Caribbean covered as well. For this example, I'm just going to show you how to make a one-year time series for a particular location. And the location we're going to focus on is Charleston, South Carolina. So I'm going to zoom in here until I can see South Carolina, and apologies if you're from South Carolina, I have no idea where that is. So there's Savannah, Georgia. I think Georgia is south of South Carolina. Yes. All right. And we're going to just choose this random station here. This is station 63351. So all of these stations have a number, okay, and they're kind of numbered according to where they are on the U.S. coastline. So if we click on that, it will bring us to that particular data set, or I call it a data set, but it's important to remember that it's output from a computer model. All right, now to start out, we're just going to click on the wave significant wave height, which is wave HS. And we're also going to click on the wave peak period, which is wave TP. Okay. And for the particular month that it's already showing, which is December of 2023, you can see that we had some bigger waves. So the purple line here, if you can see the color, is the wave height, and the green line is the wave period, and the y-axis for the period is over here on the right, and the wave height is on the left. But you can see the numbers. So on this particular day, December 17th, 6 p.m. UTC, so UTC is Universal Transverse Coordinated something or other time, basically GMT. The wave height was 5 meters and the wave period was 13 seconds. So that's actually a very large wave. So now what we're going to do is we're just going to look at what do we do if we want to look at other months or years. Okay, so I'll just show you how to make a plot for another year. So we are going to click on the export button over here, and that's going to bring up a bunch of options over here. And what we need to do is click on the generic export, and there may be other ways to do this. This is just how I've figured it out. Oh, before we get too far, one useful thing, this is the latitude and longitude of that particular station. Sometimes you need to make a map for your project, and knowing where the Wis station is allows you to put it on your project map. And then the depth here is in meters. This is the depth of that particular station. So I think all the simulations are actually done with a constant depth. They don't have the water level go up and down with tides or storms, and that's kind of a limitation for Wis. And in the Great Lakes, the water levels don't go up and down with the seasons or the years. So something to keep in mind. But offshore, that's less of an issue because the waves are generally deeper and they feel the bottom less, and the depth doesn't matter that much. Okay, so we're going to hit generic export, I believe, and then what we're going to do is we are going to go to down here, we're going to go to yearly wave height time series. And again, there's probably other ways to do this, but this is what I figured out. And we know that we're going to look at Hurricane Hugo, which hit in 1989. So we're going to try to do that entire year, and we're going to kind of look at that wave that hit in late September of '89 when Hugo was pounding the South Carolina coast. And so we can either do view or download. I'll just do view here. I think it's going to be quite tiny here, so I may eventually hit download. You have to be patient with this stuff. And then view full size, and then here it is. So let's zoom in. So what do we got here? So up at the top is always some useful information. It's the same stuff I just referenced: latitude and longitude, depth of the station, station numbers, and then the range of dates we're looking at. On the right y-axis, the red line is the peak spectral period. You can see it's pretty blocky, and that's because the model outputs discrete periods. It's not like a continuous output for the period. It's just kind of a limitation of the model. The wave height, the black line here, is continuous, and you can see that as we go from January through April of that month, we have waves that are as big as 3 meters in periods of about 4 seconds. That's probably some locally generated chop. And then as we go into April, May, June, July, August, we finally get to this monster wave here that we see. And actually all the waves in the storm are very large. This is Hurricane Hugo as far as it goes for the simulations from the Wave Information Study. And the Wave Information Study is going to use all of the meteorological information it can get to get a really good wind field, and it actually has to build the waves, from offshore in the model and then propagate them to shore and build them along the way if they're building, things like that. So it does use real wind information to do these simulations, and then of course it's validated with whatever observations you can find. But back to Hurricane Hugo, looks like we had a wave that was about 7 meters tall, so that is ginormous, right? And the period of that wave is 18 seconds or so. And if you look at that, or think about that, you're at the beach. Imagine, when you go to the Great Lakes or you go to the Gulf maybe, and you count the time between waves, it's never 17 seconds, right? So imagine this giant wave crashing on the shore, and then you're counting all the way up to 17, and then the next one hits. These are very, very long and tall waves, okay? Anyway, this is how you make this graph. If you want, you could save it from your browser here, or you could go and do the download button, and then it will show up in your downloads. Let's see, what else do we want to look at here? The other thing we can look at is the extreme analysis. I think plot is what we want. So go down here to the extremes analysis plot, and let's do view. And this one does typically take a bit of time to generate. It's doing a return period analysis on all of the peak storm waves that it has over that simulation period. So let's blow that up. And what we're looking at now is on the x-axis we have return period, and on the y-axis we have the wave height. And so it goes from 10 to the minus 1, which is a 0.1 year return period, very low return period. So I guess that would be 0.1, about a 1 month return period. So it means that on average, every month you see a wave that's about this big, 2.2 meters. On the other end of the spectrum, it fits a line to this and extrapolates all the way to the 100-year wave, and you can see that the 100-year wave height is about 8 meters. All of these points are individual storm peaks from that time series, just ordered and ranked, and then with the return period calculated. And so you can actually find that Hurricane Hugo wave on here. It's probably this one here, 7-meter wave height. That's over here. And it turns out that according to the return period statistical analysis, that would give you a return period of about 10, 20, 30, 40, 50 years. So that is basically the 50-year wave. And it's not really a coincidence. That's because the record length is about 50 years. So if you see a wave once in 50 years, we might surmise that that is the 50-year wave, and that's kind of how this analysis works. So the other cool thing about this is if you look at the bottom, it ranks all of the top 10 waves, and it gives all of the characteristics of those waves. The return period analysis only cares about the wave height, but as coastal engineers we typically also need information about the wave period, which is here, and the wave direction, which is given as theta submean. The wave direction is a compass direction. It's the direction from which the waves are propagating. And if we look at this 1989 Hurricane Hugo wave, the 7-meter 17-second wave, we can see it was coming from a direction of 97.8, which is, a compass goes, I'm going to try to do it the way you'll see it. This is 0, this is from the east is 90, from the south is 180, from the west is 270. So a wave that is coming from 97.8 is coming from the south east, just a little bit south of due east. Due east would be 90, and then 97 is a little bit southeast. And that's kind of consistent with the structure of a hurricane that would hit the coast as it's moving up the coast. So oftentimes we look at the characteristics of all these top waves, and we try to figure out what would be a reasonable period to put with a particular wave height, and where are the waves coming from when they're the biggest, because that has an important impact on the coastal design. So I think that's about what I wanted to show you here with the Wis. There's a lot of other stuff you can do over here, and I would encourage you to kind of poke around and get good at using this. One thing I didn't do is try to make a time series for a given duration or interval, so see if you can figure that out. But it seems to me that when you click the generic export over here, it kind of opens the door to a bunch of different things that you could do. So maybe that's what this custom dates here, but I'll let you play with that. Hopefully that helps to get you up and running with Wis. One thing about Wis, currently they do, or quite often they do maintenance on it, which makes it very frustrating. You go there and you expect this great product, and it may be down for days or weeks. The reason it's so frustrating is because when it works, it is so great. So it's kind of a double-edged sword. Anyway, see you later. Bye.